Okay, this is section 7.1 for MA 259, and I'm going to take a look at number 11. So hopefully as you've done your homework, you've gotten a flavor for the fact that when you're transforming from function space into this Laplace space with capital F of S, that those integrals are quite challenging and difficult and create a lot of computational effort. So what we generally do in practice is consult a table. In your book, there's a small table on page 442, a short table of Laplace transform, it says. And also in the very front cover of your book, there is a table of Laplace transforms. So if we were still in our face-to-face class, I certainly, for quizzes and tests, would hand you a copy of the Laplace transform table and say you can work off of that table. So in practice, we don't actually tend to work all these out each time. We just consult a table, generally speaking. So let's look at number 11. So I have this f of t equals the root of t plus 3t, and I rewrote this as t raised to the half plus 3 times t. So I consult my table, and I'm going to look at this part over here first. So t itself, when I apply the Laplace transform, is 1 over s squared. So I'll have this part is easy to do. And then t raised to the 1/2, I see that when I have t raised to some a, where a is bigger than -1, then I should use this gamma function of a plus 1 divided by s of a plus 1. I want to point out something here you have to be very careful of. There's also a t raised to the n, where n is bigger or equal to 0. And that n is reserved for integers, right? And then this is a, which is a non-integer, and that's something that's sort of it's not well explained sometimes, I think, in the tables, but specifically speaking, the n is reserved for integers, and the a is any number that's not an integer necessarily. So we have to use this gamma function in order to calculate what's happening with that Laplace transform. So a is equal to 1/2 in this case, so I take the Laplace of f of t, and so for this t to the half, that converts to the gamma of 1/2 plus 1 divided by s of 1/2 plus 1. And then plus 3 times t, so this is 3, and then times this t, but this t transforms to s squared. So if I simplified that, I'd have gamma of 3 over 2, s to the 3 over 2, plus 3 over s over 2. So this would really be one way to express the answer, but it turns out in some cases there are known values of this gamma function. And for example, gamma of 1 equals 1, we know that. And we also know that the gamma of x plus 1 is the same as x times the gamma of x. So if we have gamma of 1/2 plus 1, gamma of 1/2 plus 1, that's equal to 1/2, so the x comes out in front, 1/2, times the gamma of 1/2. So 1/2 times gamma of 1/2, 1/2 times gamma of 1/2. And we're told in our book that it's well known that the gamma of 1/2 is equal to this root of pi. It's one of those things that is just told to us but not explained. In face-to-face class, we would take some more time and probably try to make an argument for why that's true. So, but then gamma of 3 over 2 is equal to gamma of 1/2 plus 1, which is equal to gamma of 1/2. So since gamma of 1/2 is equal to root of pi, then gamma of 3 over 2 is equal to the root of pi divided by 2. So then our Laplace transform transforms to gamma of pi over 2 times s to the 3/2 plus 3 over s squared, where s is bigger than 0.